parallel structures. They're used by companies so that they can be very confident their system will not fail. In this particular problem, each individual component has a 20% chance of failing on its own. So it's not unusual to observe one component failing. Now it happens 20% of the time, so that's not unusual. But what about two components failing? Well, if you have two failing and they each have a 20% chance of failure on their own individually, multiply the probability that the first fails, which is 0.2, and multiply it by the probability the second fails, which is also 0.2. And you get just 4%. So that's less than 5%, which is where our cutoff is, we're going to say, for something being unusual. So yes, it would be unusual for a two-component system to fail. Oh, well then what's the chances that the two identical components system will succeed? Well, 1 minus the chances it fails, so 0.960. And then the final part of the problem, here's where a company would really be interested. They'd say, we have to have success. We can't have our components fail. So we want this probability, 99.99% chance that our components will not fail. How many identical components do we need to reach this probability? Well, if they all have a 20% chance of failure, what we're looking for, let's do 1 minus that probability right there, 0.9999. We're looking for the chance of failure to be below 0.0001. And then the chance of success will be this high that we want. So let's see how many times we have to multiply 0.2 together until we get a number below 0.0001. So if we multiply it with the 2 system, it has a 4% chance. If we have 3 components in the system, 0.008. 4 components in the system, 0.0016. A 5th component in the system, it has this percent chance that they all fail. When you put that 6th component in the system, you get a number smaller than 0.0001. So if you have 6 components, the probability of failure is right here, which is below 0.001, which means our chance of success is greater than 0.9999.